Hello everybody, my name is Craig Bennett, and today I'm starting a brand new course, and this is an IPv6. This is a multi-video course, and who is it for? This is for anyone who's looking for university level knowledge into this. I'm actually taking the information from one of my university classes and just throwing it into here because I figure some people might be interested in this, but simply can't afford a university class. Note that this is not a substitute for an actual university class, nor it is a substitute for taking the certifications if required to get a job. You need to take that on your own head. But note that I basically will be covering the exact same topics and everything for that. Now, as far as that goes, the layout of this particular video, we're going to get into IPv4 and what is it and comparing it to IPv6. The history of the internet and IPv4, history of IPv6, problems with IPv4, and IPv6 benefits. Future videos, we're going to cover stuff way more in detail. So stuff like protocols, addressing and addressing tables, neighbor discovery, and IPv6, and so on and so on and so on. But as far as that goes, note that this should be about an 11 video course. So note that, and if you're going to watch this on YouTube, then I'll have this all in a single playlist for you. But if you're watching this on Udemy, then thanks for supporting me. So as far as that goes, what is IPv4? IPv4 is simply the Internet Protocol version 4. It is the current layer 3 protocol used on the internet, and most networks use it. So your current network is probably something like 192.168 1 dot something. Well, 192 is a octet. I get into this in past videos on YouTube, so feel free to check that out. But basically, these are simply octets. There's 4 octets for IPv4. The thing to note with that, though, is that is not what it's like with IPv6. IPv6 can use characters and numbers. The actual layout is a little bit different, so just note that. So as far as that goes, IPv4 was originally described in RFC 760 in 1980 and obsoleted by RFC 790 in 1981. And you might be hearing, RFC, what is this? Well, down below in the description, I have a link to the RFCs. Just type in the number that you're curious about, and it will tell you everything that that's about. So as far as the 1990s, there were about 16 million users on the internet, whereas today, in 2017, there is a record of 3 billion, over 3 billion, so 3.7 billion hosts. This is not people. Keep in mind, you got a cell phone, you got some other device, maybe a car, you got, given your car can connect to the internet, you got your house, you got this, you got that, and you got the other. The fact is this is not people. This is purely the devices, the host, as far as that goes. We're going to get into that a little bit more. But note that the world population as of the 31st of March, it is 7.5 billion people. So I'll have a link down to this. Feel free to check that. It gets a lot more detail into that. And the fact is IPv4, it is only available to give out 4.2 billion addresses. So it's pretty much going to run out very quickly. So as far as the early years of the internet, the first internet was known as the following. I have a hard time pronouncing it, but it was made in 1969. And RFC 2235 lists many of the early events from 1957 to 1997. I'll have a link specifically to this RFC down below. It's highly interesting. I'm just going to cover a few things out of it. but it goes from Sputnik and onward. It's very interesting. So in 1982, ARPA established TCP as the protocol suite for the internet. This led to one of the first definitions of an quote-unquote internet as connected set of networks that use TCP like today. The 1983, the internet transitioned from NCP to TCP on January 1st. So basically you got internet today. In 1984, a DNS was included. It's fairly important if you're going into network engineering. It's fairly important that you actually know what a DNS is. But for those of you who don't know about DNS or don't care to go into network engineering, a DNS is simply a phone book for the internet. I have other videos onto this, but to simply explain it, if you don't know Google's IP address, you type in Google whatever, and the DNS will know how to get to it. So as far as that goes, 1984, same year, there was only 1,000 hosts. 1987, there was 10,000. 1989, there was 100,000. 92, 1 million. In 1997, there was 19 million hosts. And my favorite and most important, it was 1994. Pizza Hut found a way to make it available where users can order pizza online. But as far as the late 1970s for IPv5, basically there was a experimental protocol, and you can read through here, but basically why is there no IPv5, or at least why you might hear about IPv4, you might hear that we're going to IPv6, but you might say, well, my devices don't even have IPv5. This is actually a legitimate question because a lot of people, even in the network field, don't actually know this. The fact is IPv5 was a experimental thing. See, IPv5 was never really meant to replace IPv4, and it was actually not actually recognized as IPv5, but when it was encapsulated in IP, the ST used IP protocol number 5 and RFC 1700, and in order to prevent confusion, so if you're talking about the current IPv6, if you're saying, oh, that's IPv5, you would have to define which one you meant. It's like yelling, hey, Tom, and you got 3 Toms in a room. You got to define a little bit more on that. So prevent confusion is basically went to IPv6. No harm, no foul type of thing. So a history of IPv6, the 1993, the IETF, the Internet Engineer Task Force, I highly recommend that you join them. It's free to join and everything, part of them, announced a call for white papers for RFC 1550. The IETF formed a working group to work on IPv6. They worked on the following things. The IETF published RFC 1883 IPv6. This was obsoleted and replaced by RFC 2460 in 1998. And lastly, in 2001, the IPNG working group was renamed to the IPv6 working group. A little bit more modern, the 1996, again, the IETF, they made a test bed, and this was called 6-bone, and it was phased out in 2006. The 1999, the RIR began allocating IPv6 addresses to their customers. And just real quick, just getting a little bit off topic, how this works, because it's a little bit confusing, is the RIR has to buy their IP addresses, and a RIR hands them out to ISPs, internet service providers, and then that's where you get your address. So just real quick there. But anyways, in 2000, many vendors began adding IPv6 support to mainstream products. This includes Cisco. In 2001, Microsoft Windows XP started using IPv6. 2010, the United States federal government committed to the operation and deployment and use of IPv6. So the problem with IPv4 is IPv4 has about 4.3 billion addresses, and many people have multiple devices. The next generation simply will overload the system. Basically, if you take a look at the chart, and this goes to one of the links that I link down below, if you take a look at it, it's basically with IPv4 with 4.3 billion addresses. Here you have internet users at 3.7 billion. We're getting fairly close onto that. Many of the users have multiple devices, and next generation of people is supposed to fairly close to double the people of that we have in the world. It's really going to start in dangerous territory very quickly with food resources and few other things that scientists are trying to figure out. This is one of the things that they're trying to figure out. But it's recorded everyone from a young person to a 70-year-old on Facebook that is spending more time online equally. One of the things that was thought of is, well, if a household, like maybe some 7-year-old household, they're probably not going to use the internet, so let's take away their IP address and have their modem request an IP every time that they try to use the internet. And it turns out, well, we can't really do that because they use Facebook equally as someone who's 12 in many cases. And to put a little bit more sting into it, on Monday, January 31st, 2011, the IANA allocated the last 2 blocks of IPv4 address space to APNIC, the RIR for Asia Pacific region. This triggered an IANA policy that the remaining 5/8 addresses would be distributed equally amongst the 5 RIRs. Currently, there just simply is no more addresses. The IANA basically, again as before, they get the addresses, the RIRs, they buy the addresses from them. The ISPs, your internet service provider, they buy it from them, the RIRs. And then you get a IP address for paying, and that gets you connected to the internet. Simple as that. But while the IANA doesn't have any more addresses, the Pacific RIR does. And it's suspected that some ISPs can trade IP addresses. But with IPv6 pretty much in development, it's and ready to go in many cases, well, the fact is that's not really necessary. It's got to switch the users to IPv6. So the benefits of IPv6 is IPv6 can support around 340 trillion addresses. And it books, at least in the Cisco books that Cisco's telling the school to give us, is it's for every grain of sand on Earth. I don't really believe that, but the fact of the matter is until we get into nanotechnology, like nanorobots and stuff like that, this number is too big to really have a problem with. We would have too much of a problem if we ran into 1 trillion people on Earth, let alone 340 trillion people on Earth and the Moon and Mars and a few other places. We're not going to have really much of a problem at all with this. So as far as that goes, IPv6 provides a configurable mechanism where hosts can self-generate a routable table. And as far as the IPv6, it eliminates the need for NAT and PAT. IPv6 does not use layer 3 broadcast addresses. IPv6 has a number of tools to help with transition from IPv4 to IPv6, and again, IPv6 to IPv4. It's fairly important to note that, because the question that you might have is IPv4 dead from this? The fact of the matter is we don't have any more addresses to give out. That's a simple fact. We're definitely going to have more people with devices than addresses. So that's just basic fact. My opinion is no. IPv4 is not dead. IPv4 is probably never going to actually be dead. Let me explain why. What's going to end up happening, and this is from my experience between enterprise to home use, is let's say that you're at your house. Your house, inside of your house, is IPv4. Since it can transfer, data can transfer from IPv4 to IPv6 and again to IPv6 to IPv4. Well, what's going to end up happening is, since the outside world doesn't need to know the IP address of your exact computer, unless if for very specific reasons, the fact of the matter is the outside world, like today, only needs to know the outside box. Basically, your modem, that's the only thing that it needs to know. It needs to know how to communicate to your modem, so your modem knows how to communicate to your router, which sends a signal out through your entire house through Wi-Fi or some other method. The fact of the matter is it just needs to connect to your modem. So what's going to end up happening at the modem level is going to, from the internal of the house, is IPv4, same as normal. External of the house is going to be IPv6. So from the modem to the ISP, Internet Service Provider, that's IPv6. Now, the Internet Service Provider might force it go all the way down to your router, but your router should have the ability to convert the outside the internet traffic from IPv6 to IPv4 and convert your traffic, internal traffic, to your outside traffic. The reason why this is important is average people, they're going to be able to remember something basic like 192.168.1.1 to get into their Wi-Fi router in case something gets wrong. Like say, for example, if they need to update their Wi-Fi router, they got an email saying the Wi-Fi router has an update available. Fine. They need to actually get into the Wi-Fi router, most likely remotely, because it's in some off remote corner that they have a hard time getting into. And they really shouldn't have the hardwire to get into that. That's just bad design into itself. So with that being said, the average user is not going to remember a whole ton of numbers and letters combined, but remembering 192.168.1.1 is easy. And that's what's needed. You're not going to have 4 billion devices internal. Same thing goes if you are running at a airport or a hospital or it may be. You're not going to have 4 billion devices internally. It's just not going to happen. So you can have your internal devices, IPv4, great. And external devices, being from the router or modem out, be IPv6. That's where I see things can go. That's just more reasonable. Now, of course, you can easily go from the ISP all the way down and have IPv6. Of course, you can do that, but honestly, outside of a stream, like today, you can do that right now in most cases. But honestly, why? That's the major thing, is why. So with that being said, hopefully this has answered some questions. Again, I'm covering this in much more detail in future videos. But feel free to email me your questions or leave them in the comment section or whatever it may be. And feel free to leave a like, subscribe, whatever, and I'll see you next video. And check out the description for links that will be useful for this and for this course. But anyways, hope you have a great day.